kind of looked to me like this new configuration had begun taking on the persona of a 1950s sci-fi movie with its pale green medical looking toroid, heavy coil wire, and this crazy vertical mounting base that looks sort of Frankensteinish. But so just for fun, I added these cold cathode lights, and just for my own personal entertainment, no other purpose. They only draw 5 milliamps at 12 volts, so I'm just letting you know that up front. There's no big deal there. It's just for fun for me. Okay, lights are back on, so let's get going. First, I'm going to start this video with the elimination of a couple of misconceptions. Number one, you cannot replace the internal combustion engine in your V8 Ford with this machine. It's a pulse motor with just a reasonable amount of torque as such. It's not designed as a high horsepower motor. Okay? Number two, you cannot power your house and your two neighbors with this machine only. Again, not designed for a heavy direct load output. We'll discuss what it is designed for and how well it works. All right, now let's start. First of all, we've got the toroid generator. All right, it's not my invention. It's been around since the mid 1800s, and actually it was re-verified with modern equipment in the late 1990s to actually be true to what I'm going to tell you that it does. And what it does is pretty fascinating, because it will sidestep the counter torque of Lenz's law. Lenz's law says the induced current is such as to oppose the change in an applied field. Okay, so for those of you who aren't already familiar with this, and sorry for those of you who are, but a lot of people aren't, what that means is the induced electromagnetic field that's created in the coils here attempts to negate the applied magnetic field from the rotor magnets. Whoa, don't touch them. But unable to do this, in this configuration, due to the two opposite magnetic fluxes contained within the core of the toroid. Typically, the more current you generate, the greater the force opposing you, but not here. In fact, its power output is only limited by its overall size, the magnetic strength, both here and here in the coils, and guess what? RPM. My gosh, that makes it a really nice addition to the function of the Q series generators. So this is something that we should have been doing all along, and others do know about it, and yet you haven't seen it really appear in many devices, well, if any devices, for a long time. So we're going to use it, and I think I'm calling this the Q3, and I'll explain why. There's actually 3 different points of output, and you combine them and you get a really high pulsing output that's specifically designed to interact with the chemistry of a lead acid battery, so you can use a small amount of power and use the pulsing to charge up these lead acid batteries. That's what we're going to discuss. That's what it really shines in doing, and I'm going to explain to you why, and I'm going to show you some things that it will do. Okay, I'm going to show you a quick little demonstration of the toroid generator, but we have to remove these leads. These are 12 gauge output leads, and I use the heavier wire because, again, we are combining the toroid generator with this particular generator here, and picking up the amps from this and the volts from this, combining them. This is being pulsed, and I'm going to show you how it's being pulsed. So you get some very interesting power. This is a continuous output, whereas this is a pulsed output. But then they combine in series, and so it bumps up the voltage just a little bit. And then that also ties in with the output here from the pulse motor, which gives you a double pulse. And I'll explain how that works. So you're actually ending up with 3 pulses, dual pulses here, single pulse here, and then the continuous output. So maybe I should have called this a Q4, since you actually get 4 outputs, but it's 3 because of this motor and this generator and this generator. So anyway, so I'm going to have to use these cheap little leads here to do the demonstration. Oh yeah, by the way, this I had these in there. This is just 0.5 millimeter wall thickness of thin steel tubes, and I used them as kind of a conduit. Let me see if I can show you from this point. In between here, inside there. Anyway, back in there. Inside there, between this coil set here and the pulse motor coil set, that's just opposite, with an air gap of this much width, which is, you know, about 1.5 inches, something like that. But it's so thin that even with those giant N52 magnets on the rotor, it would pull it in, but it would seem like it gave it a little bit more torque, and it was better RPM at lower power, but the upper power was failing a bit, so I took them back out. Anyway, I just wanted to tell you, because I did mention to a couple people that I had those in there to take advantage of that electromagnetic flux that's created from the pulse coils here to pick up on the generator side here, at least on these inside coils. The outside ones just blow out into the space. So anyway, that's that. Okay, now I've permanently mounted this little meter up here for a good reason. It's actually, you know, I could use a digital meter. I've got digital meters. I got true RMS. But the thing I like about this is the fact that if you zoom in, you can see every tiny little bump in the pulse motor very, very quickly with just a glance at it. And of course, as it increases in RPM, that just exaggerates even more or less depending on how smooth or how choppy the pulse is, and you can regulate that. So anyway, pretty neat. What I did is I just mounted it to the top of the solid state relay lid, so I can take it off and remove it if I want to, if I would need to get to the wiring that's inside here for whatever reason. But this, where you see it right now, this is the smallest current draw that I can get on this 24 volt system. It's pulling. I'm going to show you how I've got a solar connection to it. That's going to be part of this video. But this is the smallest amount of current that I can draw without making this thing come to a stop. So that's it. So let's take a look at what kind of RPM we're getting at that, which is about 130 milliamps. See if I can get that thing on there. There it is. I think you can see that. Oops. New camera, I'm just getting used to it. Okay, so 497 RPM, 497.1. So pretty close to 500 RPM is the slowest that I can make this thing go. Drawing, oops, clumsy. Drawing about, each one of those marks is 120 milliamps, so you're talking it's bouncing around between, I don't know, maybe 130, 140 milliamps, something like that, at the input voltage of about 25 or 26 volts. It's a 24 volt system, but it always runs. It actually runs because of the solar. I'm using an MPPT charge controller, and I'll go over that. But it can run as low as 25 and as high as sometimes 29 volts. Usually it doesn't go much over 28. But anyway, so now for the demonstration. So seeing that we're running about 500 RPM, and we're just going to use the output from the toroid generator, and we're pulling in that 130, 140 milliamps to do it. So we'll put this under a little bit of a load here, and I'm going to use, zoom out a bit here, I'm come back up to the meter so you can see what this does when you put it under load. I'm going to use this vacuum pump. It's a pretty nice little vacuum pump, but it does require about 12 volts and 1 amp to turn. There's a lot of friction in these things, obvious. You've got this eccentric cam thing here. I mean, it's even hard to turn. You got a lot of friction right here, and then of course in the pump itself you got tons of friction. So 12 volts at 1 amp, you know, at this slow speed, you know you're not going to get that over the toroid, but with the current that it is outputting at the low voltage, I think it's probably 5 volts or maybe 8 volts or something pretty low. You know, will it even run this thing? So let's hook this up and see. Well, I know it will, but it's not very fast. All right, now I want you to see the meter, and under this load. Okay, and let me put it down here so you can see the needle. Okay, see, it's running the pump, the vacuum pump, and you can see that it might have come up just a tiny bit on the current. But it's able to run this thing with all that friction, you know, as a vacuum pump. Pretty amazing. All right, so the counter torque is the issue here that we're discussing, that we need to discuss. All right, so let me disconnect that. Now, let's take a look at the meter. Zoom back in a bit. I just go the wrong way. All right. And again, let's follow that down. Use the leads going to the toroid generator there. Okay, and let's see, we do have power. You can see that. Now what we're going to do is the ultimate resistive load, and watch how we bring this machine to a dead stop and cause that little needle to peg on the ammeter when we put this under a dead short. You ready? Okay, and there it is. Oh, wait a minute, it's not drawing any more current. Oh yeah, it is. It's definitely still running, same speed, still connected. So that's my point. It sidesteps the counter torque of Lenz's law, and it's fascinating the fact that it does that. So if we just put in a larger toroid generator on here, we're going to get some amazing results. And again, this is verified that this does actually work, and it's not some fantasy of mine or anybody else's. You know, we are running power, and we are putting a dead short on it, so it doesn't move. Interesting. Now I want you to see this really quick. You can see here on the laser tag that we're running 488.9 RPM, where we were running at 497, you know, close to 500 RPM. And the power hasn't changed, everything stays the same. The only difference is, you can see on the bench here, I've rotated the machine 45 degrees from from the east to west position that it was in, more towards north to south, and which is fascinating because when these coils point north, due north, and on the other side due south, and the rotors are turning east and west, it absolutely performs the best. That's my new rhyme. East to west performs the best. Why, I don't know. I think it probably has something to do with the gyroscopic effect of these two rotors going with the east-west rotation of the Earth, something like that. But it absolutely spins the fastest and runs the best. So it's just a point of fascination. What I want to do right now is just show you the two reed relay setup here that I've got. This particular one here is the one that pulses the pulse motor, and this one here is exactly 20 degrees out of phase with this, which pulses the generator that's on the other side, the rotor like this, that's the generator, not the toroid. So these coils are 60 degrees, exactly 60 degrees apart from each other, and these are exactly 20 degrees apart from each other, so that you get that pulsing in an angle that's out of phase with each other. There's still two very important questions I need to cover in this video. One, what will this machine do with a very small amount of input? And two, where does that input come from? First, let's talk about the pulse motor for a second. This relay here will pulse the coils 6 times per revolution. As we've talked about before in previous videos, these 6 bridge rectifiers, 3 up in here and 3 down below it, are wired independently by coil sets. 2 coils to a bridge rectifier. The input power for the pulsing comes in on the AC side. So when the coils are pulsed, the output of positive and negative in the bridge rectifier gets a jolt. Then the pulse goes off, and until it pulses again, the inductance generated by the coil sets, as that pulse is off, pulses a second time. So in essence, instead of getting 6 pulses of output on your output side, which are these ports here coming off of the pulse motor itself, you're actually getting 12. So 12 from this one and 6 from this one, which is pulsing the generator that's on the opposite side of the pulse motor. That's 18 in total. 18 pulses per revolution. All right, so let's just say we're operating at this very, very slow pace. Now, granted, it'll run way faster than this. This is as slow as I can make the machine go. That's why I showed you the demonstration of how the toroid doesn't even affect it. Doesn't act as a brake like a typical generator would do when you put it under load or when you put it under a dead short. So 18 pulses per revolution. We're talking about 500 RPM roughly, divided by 60 seconds to a minute, equals 8.33 revolutions per second of the rotors. Now take that times your 18 pulses per revolution, and you've got 150 pulses per second. And you add that with the power coming off the toroid. Do you have any idea what 150 pulses per second will do with the chemistry in a lead acid battery? It certainly will do something different than a continuous charge coming off of a typical charger or even a solar panel. That doesn't pulse, that just comes in continuous. And what you're going to get with that is you're going to get sulfates on your lead plates. When you pulse with even a small amount of current, you're going to keep those batteries rejuvenated while you're charging them. Oh yes, I've heard some say, oh yes, but that's just a surface charge. You know what? That's baloney, because when those batteries charge up to 12.5 to 13 volts and have the standing voltage of that and deliver all that power, that's no surface voltage. That's a good solid charge. And that's what this machine does. This doesn't run a nuclear sub. This doesn't, you can't change this for the motor in your car. All those things are nonsense. This thing does a job, and it does it well. Okay, so that's what the object is of this machine. That's what it does. Now, where does that small amount of power come from? Before we touch on that, let me just one final time say that that we're running right now at 130 milliamps at roughly 25 volts. If you bring that up, if you bring your RPM up from 500 to let's just say 1,000 RPM, this thing will cap out around 1,200 RPM. So let's just say you bring it up to 1,000 RPM, you're not even burning an amp. It runs that at about 750 to 800 milliamps, and will give you not 150 pulses per second, but 300 pulses per second, because you've doubled the RPM. So 300 pulses per second, my gosh, can you imagine that? That's just amazing. If you've ever built a device with a bifilar coil and you've gotten the back EMF spikes, and to see what that does to a battery, I'm going to show you how to do that as well with this machine. And that's besides the normal pulsing to charge a standard bank of 24 volt batteries, or 12 volt batteries that are connected in series parallel for 24 volts. All right, now we're going to get to where the power comes from. Now we're down to the input power. Where does it come from, and what does it do? What is it doing? So we're still pulling in very small amount of current on the ammeter. And where is it coming from? Right here. This is your input. And what it's doing right now, since I removed the sine wave peak generator, I have connected the 3 banks of caps together so that they will provide 27 to 28 volts and level off the power that's brought in from here. And where does this come from? Follow it down here. It's coming from my MPPT solar charge controller. I have one solar panel. This wire here runs up to the ceiling, runs through the roof and up to one solar panel. It's a 280 watt solar panel. Nice one from Grape Solar out in Oregon. This charge controller, MPPT, stands for maximum power point tracking. And let me just show you this, if I can zoom in a little bit. So this connection here is coming off the solar panel right here. This one here is coming out of the controller, going directly to your bank of batteries, which are 4 deep cycle batteries below such on this cart. And of course I've got it running on the positive side here through a 25 amp breaker or fuse, I mean. So, which is kind of nice, because if it blows, it turns red, so you can tell right away. But it doesn't. Anyway, there's the negative. And then here is an auxiliary port, output port, that primarily gets its power from the solar panel itself, and not necessarily from your bank of batteries down below here. It will if it needs to, but in most cases it doesn't, because the panel is strong enough to keep those batteries charged, depending on how you're pulling a load on them. And I'm going to show you what I do. So over here, then finally this last port is just for communications to this meter, which is pretty nice. And this shows you right now that that's the auxiliary, and I'm pulling 28.3 volts. No amps. It bounces around because, again, what it's doing is it's putting power into the capacitors and then flattens them out, and all the energy from the capacitor banks are what go down and pulse the pulse motor, through the engagement of the reed relay. So, but it's all coming from these caps, and all that is coming from this. So here we are. Now let's go one over. All right, there's the battery. Let's go over to the solar panel. Okay, this is how this works. So the solar panel right now, it is almost 6:30 in the afternoon, so we're not generating much power, but it doesn't matter, because this indicates that the battery's full. All the bars are black. It's the battery's full. I'm not drawing anything off of it. So the solar panel is generating 32.5 volts, and what is the bank of batteries doing with that? It's knocking the charge controller is knocking it down to 28.5 at 0.8 amps, and that rises and falls because, again, the batteries are full. So it's just trickling of power in there, and I've already shown you this. Okay, now what do you do with the power off those batteries? I would suggest, I got this system recently, and this is really nice. This is a Go Power inverter. It's a 2 kW inverter that's a pure sine wave. Very, very nice. It's I think, well, it says Victoria, BC on it. I don't know if it's manufactured there or they import it from China, but it's a nice unit. And then I bought this extra meter here that shows you your battery output and volts and current and some other information here, whether you got the power saver on and so forth. It's really a nice inverter. This is obviously the back side. Make sure if you get one of these that you use this really heavy gauge. This is what, 4, oops, upside down. You read that? Yeah, 4 gauge. It's 4 gauge battery cable, you know, like you'd have in vehicles. Very strong stuff, but it'll carry a lot of amps. So because this will give you up to 4 kW peak, you know, if you need a big boost of power, but 2000 kW continuous. So it's a pretty nice unit. And I made this male-to-male pigtail here so that you can take, dropped it again. Nice. Let me just set this up here, spin it around. Here's the front side. It's got ground fault, a couple of ground fault outlets there. And then with this pigtail thing, I can plug this into this and go into the meter. As long as the mains are off, you got to make sure the mains are, if you have, unless you're off the grid already, put this in to a meter with no, you know, not connected to any mains coming in, and you can throw breakers and isolate an area and just throw your power into those particular rooms. But with pure sine wave, you can run your computers, TVs, any, you know, sophisticated electronics with that. It has a nice power saver here, so if you've got things that recycle on and off, refrigerator, small air conditioners or whatever, it will shut this off. It'll shut the fans down and just goes into standby mode until it senses that power is needed from the device. When it kicks back on, it just gives a trickle charge in there, and then it gives full charge, and bam, it does its thing and then shuts off. So it's a really nice feature. It's a very good unit. Anyway, so that's what I'm doing. You can use this for emergency power's sake, or you can have more, obviously. Depends on the bank of batteries that you've got, how many you're charging up, whether you've got you know, one solar panel like I've got, or you have several solar panels, and you're using a machine like this to charge additional banks of batteries from a small amount of extra output that you get from this auxiliary port on a really good MPPT controller. These are not cheap. I'm not saying you get these for free, but you get what you pay for. And this is the way to go. If you want the maximum efficiency, you're going to need this. You're going to need a good quality one of these, and getting this auxiliary port is really key to running something like this to take that power to the next level and charge up an additional bank of batteries. You don't just need these 4 like this. Maybe you've got 8 or 10 or 12 or whatever your power demand is. But this is a real good system, and this works great. So that's how I'm using it. Oh, one final note on that is if you get a setup like this, make absolutely sure you get a 24 volt system. This is designed to be operated with 24 volts, as is this particular MPPT charge controller as well, 24 volts. And the reason they're making them 24 volts is because your efficiencies jump way up over that of a 12 volt system. So look for that if you're thinking about going that route. Now, one last note. Let's see this thing start back up from a dead stop. Obviously, it's not turning right now, and we're just going to disconnect this input power, because it will run quite some time off just these caps only, and even from a dead start, or dead stop, I should say. Okay, so let's just give this a little spin and come over here and slide the reed switch to engage, and see right now it's at 1.2 amps. What's really amazing is it'll take 5 minutes, sometimes 10 minutes, and that 1.2 amps will end up being down around 0.6 or 0.7. See, it rises a little bit and then it starts to fall. But let's see where we're at right now with the TAC at 1.2. We're only at 722 RPM. So as that falls, As the current falls, you can see it's starting to fall. Like I said, it takes 5 minutes, sometimes 10 minutes. It'll come all the way down, and as it does, your RPM will come up. It's the strangest darn thing you ever seen. It's like the opposite of what it should do, but that's what it does. Let's see where we're at now. Well, 720. Oops. Let me get that on there. 730. 731. You see how it's rising? It just keeps rising and rising and rising and rising as the current drops and drops and drops. You just gotta love this stuff. It's crazy, but it's cool. Wanted to show you that. Oh, and it's running just on the caps. Okay, I just pushed the reed switch just a little bit more one more time, and we're back to drawing. I pushed it back up where it was drawing 1.2, and it's starting to come down a little bit. Well, it's bouncing around a little bit, but we're up to 1,002 RPM at this point, and that should continue to come down as the RPM rises. Recently, a very good friend of mine from New York asked me if my machine would desulfate batteries. I said, I don't know. I haven't tried. And it was a short time after that this battery in my Toyota that had been in service for 7 years gave out. It just no longer would hold a charge. 7 years, that's a pretty good time. But I was going to take it in for a core charge after I replaced the battery, you know, and just get whatever, $10 or whatever off of that. And I thought, well, wait a minute, maybe it's sulfated. Maybe this is my opportunity to give this a test. So here's the setup. Wire number 1, wire number 2, and over here wire number 3, and one little diode. That's it. That's all you need. That's all you need. Now, this wire over here, this yellow wire, all it does is it jumps the diode of the negative power that goes into the solid state relay. This is the input side. So you jump that diode. Then on the output side that's pulsing of the negative from the solid state relay on the load, that negative comes in, and of course it connects to these AC ports that are in series on one AC side of each of these bridge rectifiers. So I've just connected it here. You can connect it on the solid state relay if you want, or you can connect it here. I just did this for convenience. And it has the diode on the end. And it's one little diode. That's all it takes, okay? And so we've got the jumper is in place. We've got this. And the red one over here, this wire, is connected to the positive input right there. Positive input, whether it's the caps only or whether you've got it connected to the solar panel or whatever. That's your positive input. That positive wire goes to your negative. Now let me back up for a second. I'll go ahead and put that on there. When I brought this battery in and I put it on the bench and I tested it with the meter, it only read 8.5 volts. I put it on a standard charger. It charged up to about I don't know, 9.5 volts, something like that, and that was it. It just wouldn't take a charge. It was just sulfated. So what I did is I did what I'm showing you here. I'm going to go ahead and put this on here now with the diode. Now it slows the machine down. You can hear it, but look at the meter. It was at 12.56 standing volts because I had conditioned it, and all I did it was like 4, maybe 5 times. I did this, then I drained the battery down. The first time I think I brought the voltage up using this system with these 3 wires and the diode. I think I brought the battery up to about 10 volts, something like that. Then I brought it back down, but not to the 8.5. I brought it down to about 9 volts. and just put a heavy load on it, you know, brought it right down, and then I put this back on and I brought it back up and it charged a little higher than 10. It was like 10 and a half. So I repeated the cycle, and by the time I did it the 4th or 5th time, it charged up to about 12.8, I think it was, or maybe 13, something like that, and then it settled down to 12.56, and that's where you saw it. And it's a standing voltage. I put a load on it, and it takes the load. It doesn't just kill the battery. It keeps it running. In fact, I think it's better than new. I think it'll run it for a longer period of time. Now you can see I don't need to do this now because this battery is ready to go back into standard service and be charged with a standard charger if you want. Because this is just primarily just for reconditioning that battery. There's no sense in these batteries going to a landfill or you know, you getting $10 for it as a core charge. This is like getting a free battery. Here it's already 7 years old. I would imagine that using this system and fixing this battery over and over and over, it'll probably last you your lifetime, maybe longer. I don't think there's any reason. I don't think the lead plates aren't going anywhere. The sulfate buildup on those plates, the lead's still fine. Knock that sulfur off, or those sulfates off, and you've got a battery that's as good as, if not better than new. This thing, I've actually tried charging it up pretty high, and it'll go up to 15, 16 volts if you let it. But it'll settle down to 13, 14 volts, but I don't want to, you know, push it and tax it because I want to use it. It's a decent battery, and they're expensive, so you know, might as well put it in the system and work it with this system and put it in another bank. But you can see the voltage is still rising, and if you read the voltage that's coming off of this, it's actually very low. Coming directly off. Let's just disconnect that and put it on there. See what it reads? 5.8 volts. It was like 5.8 volts when we first pulled it off. 5.8 volts. And yet, because that meter is just way too slow to pick up the spikes that are coming in there off those 12 coils on the pulse motor. And there you have it. The system works.